Start the record. There we go. Okay, now we're rolling. So yeah, these are the parts of the machine. Anyone need more time on this slide? Looks like no. So let's go ahead and move on. Principle of machine. What are it says, what is the principle of a machine? Write the equation. And there's several equations here. This is the main one. Let me kind of star it here. This one here. This is the real equation that we're talking about. But the other ones kind of help explain what we're actually going for. Um, so remember, from conservation of energy, work input equals work output. And input force times input distance equals output force and output distance. So what you want to do is, you don't need to write this first one, but you should probably write these two that I'm starring. Um, if you can multiply the force, the work has to be the same. So you would decrease the distance. Like if you have a lever or a pulley, I could lift something that's, 10 times heavier than I could really lift it if it was hooked up to a pulley, but it would only go 1/10 the distance, if that makes sense. But really, these two equations are kind of saying the same thing. This one's just in words, and this one isn't exactly in variables, but you get the idea. You could put F1 D1 equals F2 D2, something like that. Like if you wanted to write it like this. Really hard to write on this screen. I can't wait for you guys to come back. I'm so sick of these Zoom meetings, by the way. I apologize. I know they're not as good as lectures, but you guys will be back in a week. So just one more week. All right. Anyone need more time?
I do.
Okay.
Okay, I'm good.
All right. Then we'll go ahead and move on. This is they're talking about some real simple machines. So we're only going to talk about a couple, really levers and pulleys. Although there are like gears, there's lots of different simple machines that we use all the time. A lever is probably the most simple machine. It's really just like a piece of wood or metal or some kind of board, and then you put a fulcrum, not right in the middle. If it's right in the middle, then it's like a one of those, a seesaw, it doesn't really multiply the force of the distance. But if you put it closer to one end, then what happens is you can use less of a force, a greater distance to move something that's really heavy a small distance. So it allows a small force over a large distance and a large force over a small distance. So this is kind of the key bullet right there. So what it's saying is that a small force over a large distance. So like, let's say I wanted to lift my car. Um, I would need a really long stick with the fulcrum, and I'd have to move that stick a really long distance, and that car would only move a small distance, but it would have a great force, and you'd be able to actually move the car. The way that those car jacks work, that when you like have a flat tire and stuff, it doesn't exactly, it's kind of like a lever. It uses rotational motion to help lift the device, but it's basically the same idea. All right, anyone need more time? No? Okay, next slide. Pulley. So pulley, it's like a lever or a lever with equal arms. It changes the direction of the input force. So like this one pulls down, you pull down to lift up, but it can also allow a load to be lifted with half the input force. So there's one other slide on pulleys. Let me look at it before I tell you what to write. Um, let's just write here. It can change the, sorry, it can change the input force. Oops, I'm telling you. It can change the direction of the input force, and it can, and then the next one thing we'll write is really this example, but it's better written on the next slide. Anyone need more time? Okay, let's go to the next slide. We'll write the second part of this box. And I actually did kind of, it multiplies the force. So it's the same thing as a lever, basically. You can multiply the force. You're going to have to lift more distance, but you can multiply the force. And let me show you guys an example of that before we move on, just to make this make a little more sense. I skipped this page in the workbook because it's kind of, it's really hard to do on your own. But I'll share it with you real quick and we'll just look at this pulley example. Sorry, one second. I'll be back. Here we go. All right, so here is uh, some questions about levers. So here, this person has it set up so it just changes the direction of the force. So they'd actually have to pull down 100 newtons to lift this 100. On this one, you've got half of the weight of this block supported by this string here. So this guy would only have to pull 50 newtons to lift this 100 Newton block up, but he'd have to pull it twice as far. This one is similar, although let's see, it's got two strings, so this would also be 50 newtons. And then this one right here is kind of a good example. There are 1, 2, 3, 4, 5, 6 strings supporting this weight. So he would only have to pull down with 100 newtons of force to lift this 600 Newton weight, but he'd have to pull down 6 times as far as he wanted it to move to get it to move far enough, if that makes sense. Any questions on pulleys? No? All right. We'll go back to the lecture. Sorry, struggling here. There we go. All right, next slide. An ideal pulley system, a woman lifts a 100 Newton crate by pulling a rope downward with a force of 25 newtons. For every 1 meter length of rope she pulls down, the crate rises. Let's see. We got a couple people that aren't that visible, so I'm going to call on them. Tucker, are you there? I didn't think so. We'll go with who wants? Anyone want to take a guess? No. How about Ian? What do you think?
Um, None of the above.
Okay, so that's not a, why do you think that?
Um, I think that The answer is C.
Okay, that is actually correct. And how did you come to that answer? It's common sense, or did you use like a specific way of thinking?
Um, Common sense.
Okay, and it's you can lots of times figure these problems out just with common sense. But if you remember, force times distance input equals force times distance output. So if she lifts a 100 Newton crate by pulling down with 25 Newtons, that's 25 Newtons of force, times the distance it goes, equals, this would be D1, for example. It's a 100 Newton crate, so the output is 100 Newtons of force times distance 2. And what you'll find is that the ratio of distance 1 to distance 2 is 25 to 100. So it is C, 25 centimeters. Good job. Anyone have any questions on that? No? All right. Next question or next slide. Efficiency. What's the efficiency of a machine? And this is a pretty easy equation, but you do need to understand how to do it. It's useful energy output divided by total energy input. Useful energy output divided by total energy input. And it's how much work put into a machine is how much of that work is actually converted into useful work output. All right, we're getting there, guys. We're almost done. We only got a few more things to go over, and then we'll be done for the day. Um, Anyone need more time on this slide? No? All right, next slide. So here's a good question about efficiency. A certain machine is 30% efficient. This means the machine will convert what? 30% of the energy into useful work, 70% will be wasted. 70% of the energy into useful work, 30% will be wasted, both or neither. Well, it can't be both because these literally are two opposite things. So hopefully you can rule that one out. It's A, B, or D. Let's go with Emmy this time. What do you think?
Is it B?
So remember the equation, useful energy output divided by total energy input. So only 30% of it it's only 30% efficient.
So A?
A is correct. Yes, yes. A is
Okay.
correct. It the 30% is useful and 70% is wasted. Now you may think this is a really inefficient engine or machine that's doing this, but this is about what a internal combustion engine, how efficient that is. We lose a lot of the energy to heat in like engines in your cars, a gasoline powered engine. All right, good job. Recycled energy. They're just going to write a little bit about this. Recycled energy is when you use energy that would otherwise be wasted. So, for example, there's a power plant in New York that creates energy. It wastes a lot of that. It creates electricity, sorry. In the process of creating electricity, it's not very efficient. and about 30% of the energy is wasted, is turned into heat and wasted. So instead of just letting that heat go out into the environment and not do anything, they use it to heat buildings. So it's just using energy that would have otherwise been wasted. I'm trying to think of another example. When we get to nuclear power way later in the year, we'll talk about, or nuclear fusion, sorry, and fission. We'll talk about these breeder reactors that use what the waste of one nuclear power plant can be used as the fuel for a different type of nuclear power plant. All right, sorry, did anyone need more time on this slide? No? Okay. Next slide. Energy for life. Our body is a type of machine. It needs energy or else it stops being alive. Our cells feed on hydrocarbons. What a hydrocarbon is, it's just a molecule that's made up of carbons. Trying to draw on this and it's not working very well this morning. Carbons and hydrogens. Anyone, what's the most common hydrocarbon used for our energy? Anyone know? Could also have oxygens in it, by the way. Starts with a G. Come on, think back to biology. I can't throw high chews through the screen. I wish I could. Glucose, right? Glucose is the most common. Oh, did somebody write it? Let's see. Genes. Genes are not hydrocarbons. I mean, they kind of, well, genes are biological macromolecules or, DNA. But that's not really used for energy very much. It's more like glucose. We can use proteins. We can use fats. We don't generally use DNA very much for energy. Glucose is a sugar, by the way. All right, next slide. Sources of energy. Now we're going to write about these 4 sources of energy, and then we're going to try to name some other ones. So the most plentiful source of energy is the sun. The sun can be used to evaporate water. Water falls as rain. Rain turns into rivers, and rivers then get dammed, and they turn generators and turbines that can generate electricity. We can use photovoltaic cells. These are called solar panels.
I have a question.
Yeah, go ahead.
Do we have to write all these examples?
The examples, if I look at your guided notes, they should be in there, right?
Not on the Canvas copy.
Really? I thought I added it. Let's see here. Let me look.
Well, it says sun, but I don't know if we have to write all the examples.
Yeah, you got to write the important stuff, the stuff that I kind of emphasize. So, what I would write if I was you guys, let me share my screen again, is I would write that sun can be used to in solar panels. It creates wind and it also creates weather. That's what I would say. And what's happening with climate change is we're not getting more sun, we're just keeping in more of the sun's energy. And that's so people may wonder, why does climate change lead to more severe hurricanes? Well, think of it this way. heat is a form of energy. You're adding heat to the oceans that where those hurricanes start, that's adding energy to the hurricanes. So they're just going to get more and more severe as time goes on, as climate change gets worse and worse. That doesn't mean that every single year will be like the worst hurricane year of all time, but it means that as a general trend, we'll see the hurricane seasons getting more and more destructive. It'll be interesting to see what people that live in those regions that are constantly hit by hurricanes decide to do um, over time. All right, anyone need more time on this slide? All right, next one. Oh, this is a solar panel. Oh, I wanted to say this. Just this year, like maybe 3 months ago, 2 months ago, they came out with new solar panels that were 60% more efficient. So that could be a real game changer. One of the problems with solar panels, and you guys will do some research on this next class, is they don't work when it's really cloudy very well, and they don't work at night. Um, and honestly, they haven't and historically been the most efficient way to generate energy. And it's hard to store that energy. But our battery technology is getting a lot better, and if solar panels can get more efficient, then this could become a more economically like sound way to generate energy. All right, fuel cells. These are basically the opposites of a battery. A fuel cell, and all you really need to write here, I don't think you need to write a lot. No, you don't need to write a lot. Is that it generates electricity similar to a battery. Just write that.
So is it the same or the opposite?
So it's the opposite, but I mean it's similar in that it's just the opposite process. Like you just take the battery equation and you just reverse it. And we'll get into that a little more when we talk about electricity, but it's hard to explain without having some real fundamentals of electricity down. All right, anyone need more time? Okay. The next one is one that you've heard of, and one that I think should be used more commonly in this country is nuclear power. We're calling this concentrated energy, but it's really nuclear power. This would be nuclear fission. We did just barely have a process of nuclear fusion that generated more electricity than it used, but that is still kind of theoretical. Fusion is where things join together. Fission is where things split apart. It's stored in uranium and plutonium, which can be relatively hard to get, and they're super radioactive. That's why nuclear power is dangerous. But it's a really efficient way to generate electricity. And basically what they do is they use the nuclear energy that comes from these nuclear reactions to generate heat, which boils water, which turns a turbine, which generates electricity. And then I believe anyone need more time on this slide? Not a ton to write. I believe the last type of energy, and then we'll just come up with some other ones, is geothermal energy. And basically what this does is it takes water that, as you get closer to the center of the earth, it gets hotter and hotter. So water that's way underground is really hot, kind of like at Yellowstone, where that water comes to the surface sometimes. Basically what geothermal power does is you drill down to that really hot water, and then you have it pumped up. It creates steam, turns a turbine, and then goes back down when it's cool, and then gets reheated, and it just cycles like that. So it uses hot water from deep in the earth to generate electricity, would be what I would write.
Can you say that again?
It uses hot water from deep in the earth to generate electricity. And that's how most power plants work. If you guys have ever driven even past Las Vegas and you've seen those like little towers that are down there that have all the mirrors pointing sunlight at them, all that's doing is taking the sunlight that hits those mirrors, directing them onto that tower and boiling water and turning a turbine and generating electricity. Anyone need more time on this slide? Believe that's it for slides. We have one more thing to take notes on, which you don't need to, I don't need to be sharing my screen with you for. What are some other sources of energy or electricity? What do you think the main one is in Utah that we use? Any guesses? You can just write them in the chat. Go ahead, Jacob.
Coal.
Coal is the, yeah, Peter, yeah, you guys are right. So coal is a source of energy, and it is the main one we use in Utah to generate electricity. Some other ones that we haven't talked about, we didn't really, I mean, I kind of talked about dams with the sun, but we didn't really talk about dams like Hoover Dam and Glen Canyon Dam for Lake Mead and Lake Powell generate tons of electricity for southern Utah and for Las Vegas. There's other sources of energy. Anyone think of any others? What other ones do you guys know of? Some of you guys might have already taken chemistry, might have done this before, or environmental science. Well, we'll do more on this. If nobody has anything else, we'll do more on this on Wednesday. It'll be kind of a more of a research day as far as this goes. All right. So that's it for the lecture today, guys. Make sure you get those notes turned in by the end of the day. And what we're gonna do now is we are going to do a Bill Nye video worksheet. So if you go to Canvas, I'm gonna share my screen with you again. Where'd my Canvas? Here it is. Go back to the home page. And you're gonna do this Bill Nye Simple Machines video worksheet. It's about 20 minutes and there's 15 questions. Each question is worth a third of a point because it's worth 5 points total. It says it's 30 minutes, but it's not. It's only 20. Maybe 22, because I think you do have to actually listen to the music this time because you got to get 4 simple machines from the machinery video. Anyone that needs, if any of you guys have submitted the workbook and not done very well on it, and you want to remediate certain things, what I'm going to do right now is either way, you got to stay on the Zoom for 15 more minutes, but I am going to create a breakout room, and anybody that wants to join the breakout room can do so, and I'm just going to create one breakout room, and I'll just take questions there as far as the on the workbook. And otherwise, you guys just stay on this Zoom session and work on the video. So anyone that needs help on the workbook, please, if you want to, I created a breakout room. You can go join that. As soon as people are there, I will join them. Can you have your cameras off? Not if you want to be marked present. It's just the rule. You got to have your cameras on 90% of the class. Is there anybody that needs help on the workbook, or did you guys all do pretty well? All right, well, if nobody needs help, then you guys can just have this time to work. I'll stay on here in case anyone has questions until 8:50. At that point, you're welcome to sign off. And good luck with the rest of the day. We got 2 more Zoom classes before we are back in person. I do have somebody in the breakout room, so I'm going to go to join room 1. I'll be back in here in this room in just a minute. Well, I guess I'm the only one in here. There was nobody in the breakout room. Says he's in there.
What's the breakout room for?